So with chemical reactions, we use, which are actually chemical changes, we use chemical equations. And so you can think of chemical equations as recipes for chemical reactions. Just like you have a recipe to make a cake or cookies or a meal, you have recipes for chemical reactions. And the recipe is made up of two components. It's made up of the reactants, which is what you start with, and they're on the left side. And it's made up of the products, which is what you end up with, and they're on the right side. And so there's an arrow in the middle that shows you go from reactants to products. Now, one thing you need to remember about chemical reactions is that in chemical reactions, atoms are neither created or destroyed. So however many atoms you start with on the reactant side, you have to have that many atoms of that many atoms on the product side. So it has to be what we call a balanced equation. So if you have two hydrogens on one side, you got to have somewhere two hydrogens on the other side. So the atoms must be accounted for. And that's why when we talk about chemical equations, we're going to be talking about balancing chemical equations, because we got to have the same number of atoms of each type of element on both sides of the equation. Now, for chemical reactions, we also have to indicate the physical states of our reactants and products. So the common subscripts that we use for physical states are things like G for gas. So if something is a gas, we have to indicate that it is gas. S for solid, and L for liquid. These three are pretty much straightforward, but AQ is for aqueous. So what aqueous means is something is in water. So if you see a compound and it has a subscript aqueous next to it, that means it's been dissolved in water. Likewise, if you see an ion in a chemical equation, usually it has AQ around it because ions only exist in solutions. So they're always going to have an aqueous sign. Now we have a few examples of writing chemical equations. So we have this reaction of methane with oxygen to form carbon dioxide and water vapor. Now methane is typically found in the gaseous state. So methane here is a gas, oxygen is a gas, and when it forms carbon dioxide is generally a gas, and of course water vapor is a gas. So all four of these are gaseous components. And so methane and oxygen are our reactants, because that's what we're reacting to form, means the products, carbon dioxide and water vapor. Now again, here we're just writing the equation, we're not balancing them yet. So again, methane, oxygen, carbon dioxide, and water vapor are all in the gaseous state. So we use the subscript G to indicate that they're gases. In the next example, we have a reaction of solid potassium with water. And then you see it here again, to form means we're going to products, hydrogen gas and potassium hydroxide dissolved in water. And so our reactants are solid potassium and water. So water is a liquid, solid potassium means we use the subscript S, yields hydrogen gas and potassium hydroxide dissolved in water, indicates that it is a aqueous product. And so again, reactants are what we start with, products are what we form. Now here we've just written the chemical equations, but next we're going to learn how to balance them, because as we stated earlier, we have to account for all of the atoms on the reactants and products sides. So with balancing equations, I can give you tips, which we'll see, but it's mainly through practice that you get better at balancing equations. And I can give you tips to go through that kind of helps ease the process. But for the main thing, you have to just practice like you do when you're making a recipe. You have to keep on trying. So the first thing we need to note is that the atoms are conserved in the chemical reaction. So we have to make sure that we have the same number of atoms on both sides of the equation. Bullet 2 is very important because this is a common issue that I see a lot of students do, is that we never change the formulas of the compounds when writing the balanced equation. What this means is that you never change the subscripts. That's why I have it in capital letters. Never, ever, ever change the subscripts in your reactants and products. When you change the subscripts, you change the compound. So for example, O2 is something that we breathe, oxygen gas, but if I change it from a 2 to a 3, I no longer have oxygen gas, I have ozone. And if you breathe in ozone, it's not the same as breathing in oxygen gas. Likewise, if we have H2O, which is water, something we drink, if I change that O from a 1 to a 2 and say H2O2, now it's hydrogen peroxide. You don't drink hydrogen peroxide, you use it to treat wounds. And so when we're balancing chemical equations, we do not change the subscripts. We only change the coefficients, and the coefficients are the numbers in front of the reactants and products. So when you start a balancing equation, the coefficients start off to be 1. So if a coefficient is 1, you don't put 1 there. It's understood that it is 1. As you balance, you change the coefficients. So again, we're going to change the number in front of the reactants and products. Now, a few guidelines to go by, and I'll give you more guidelines as we do more examples. But here, if we look at the first reaction, we have hydrogen gas plus oxygen gas gives us H2O liquid. So the first thing we want to do is determine the number of each element on both sides of the equation. So on the reactant side, we have 2 hydrogen and 2 oxygen. So that subscript means we have 2 of each. On the product side, we have 2 hydrogen and 1 oxygen. So sometimes just by looking at the number of each type of atom you have on both sides of the equation, you can kind of determine what to start with balancing. So since the hydrogen is balanced, the oxygen is not, the first step would be to balance the oxygen. So we have 2 oxygen on one side, we have 1 oxygen on the other side. So to turn this 1 into 2, we're going to have to put a coefficient of 2 in front of water. Now this 2 gets distributed to the hydrogen and to the oxygen. So now we have 2 oxygen, but you see our hydrogens change to 4. So our product side, we have 4 hydrogen. On our reactant side, we have 2. So now we need to turn this 2 hydrogens into 4. So we're going to put a coefficient of 2 in front of the hydrogen. Now the hydrogen goes from 2 to 4. And you see now that we have the same number of each type of element on both sides of the reaction. So this is a balanced chemical reaction. Now again, for example, the coefficients of your reactants and products, the lowest common multiple between, or the common multiple between all your coefficients should be 1. If it's not 1, you need to factor out what is the common multiple until you get a common factor of 1. So 2 to 1 to 2 is a good set of coefficients. So it's understood that there's a 1 in front of the O2. Now if we go to the next equation, we have C2H5OH plus O2 gives us CO2 and H2O. So we're going to determine the number of each type of elements on both sides of the equation. So we got 2 carbon, 6 hydrogen, 3 oxygen. And on the product side, we have 1 carbon, 3 oxygen, 2 hydrogen. So now when you're looking at this, you notice that, hey, both the carbon, and I wrote them out of order, and the hydrogen are not balanced. So the question arises, what do we balance first? Do we balance the carbon or the hydrogen? And this comes up with the next tip. So the next tip is that generally when you have different elements that need to be balanced, you generally start with the non-hydrogen or oxygen element first, and you wait to the end to do those. So using that tip, what we're going to do first is balance the carbon. So we have 2 carbon on this side, 1 carbon on this side, on the product side, so we're going to add a 2 in front of CO2. And again, that 2 gets distributed to the carbon and to the oxygen. So now the carbon becomes 2. So 2 times 2 is 4. 4 plus 1 oxygen over here makes 5. So now our carbon are balanced, but our oxygen is not balanced. And the hydrogen's not balanced as well. Now this leads us to the next tip. The next tip is when you have 2 or more elements that need to be balanced, it's best to balance the element that only occurs in one product and reactant versus an element that occurs in multiple products and reactants. So let me say that again. So the next tip is it's always better to balance elements that occur in one reactant and product, then balance the ones that occur in multiple reactants and products. So for example here, hydrogen is only in one reactant and one product, but you see oxygen is in every reactant and product. So using that tip, we're going to balance hydrogen next. So we have 6 hydrogen on one side, 2 hydrogen on the other side. So we're going to have to put a 3 in front of the H2O to make 6 hydrogen. So the 3 gets distributed to the H and to the O. So now we have 6 hydrogen, but we have 3 oxygen for the water and 4 oxygen for CO2. So now our total oxygen is 7. So we have 7 oxygen on the product side, 3 oxygen on the reactant side. But notice on the reactant side, it's not all 3 oxygens on the same reactant. We have 1 oxygen on one reactant and we have 2 oxygen on another. So what we can do is since there's one reactant that has 1 oxygen, the other one has 2, we can actually balance the oxygen so they have a total number of 7 by adding a 3 in front of the O2. So if we put a 3 here, now this becomes 6. And you see we now have a total of 7 oxygen. So this would be a balanced chemical equation. So we'll go through these 4 examples. So in the first example, we have NO plus H2 gives us N2 plus H2O. So the first thing we want to do is determine the number of each element on both sides of the equation. So we have 1 nitrogen, 1 oxygen, 2 hydrogen on the reactant side. On the product side, we have 2 nitrogen, 1 oxygen, 2 hydrogen. So right off the bat, we see that oxygen and hydrogen are balanced, nitrogen is not. So on the product side, we have 2 nitrogen. So on the reactant side, we need 2 nitrogen. So what we're going to do is we're going to put a 2 in front of NO. So again, that 2 gets distributed to the nitrogen and to the oxygen. So now we have 2 nitrogen and 2 oxygen. So now this directs us to what we need to balance next. So you see on the reactant side, we have 2 oxygen. On the product side, we have 1 oxygen. Secondly, the hydrogen are still balanced. So now we need to balance the oxygen. So we need to put a 2 in front of H2O. And again, the 2 gets distributed to the H and to the O, or oxygen. So now we have 2 oxygen, but our hydrogen increased to 4. So now we go back to the reactant side. So we have 2 hydrogen. We need to make it 4, so we're going to put a 2 in front of H2. And so 2 times 2 gives us 4. And so this is the balanced chemical equation for this reaction. So what this equation is saying is that for every 2 moles of NO and 2 moles of H2 that you react, you form 1 mole of N2 and 2 moles of H2O. Now moving to the second example, we have iron plus oxygen gives us iron oxide. This is the chemical change that occurs when rust forms. Iron 3 oxide is commonly referred to as rust. And so we determine the number of each element on both sides of the equation. So we have 1 iron, 2 oxygen, and we have 2 iron and 3 oxygen. Now here I have to introduce another tip or guideline to follow, is that you notice that both of these are not balanced. Iron is not balanced, oxygen is not balanced. But you'll notice that the iron on the reactant side has a subscript of 1. There's only 1 iron. So anything we put in front of iron, we can balance it. Now oxygen on the reactant side has a subscript of 2. Iron on the product side has a subscript of 2. But again, the iron on the reactant side doesn't have a subscript, so whatever iron is on the product side, we can easily balance it on the reactant side. But you notice here that oxygen on the product side has a subscript of 3. So in this case, since there's an even-odd discrepancy between the oxygen, it's best to balance the oxygen first and then balance the iron, because whatever iron is on the product side is going to be easy to balance it on the reactant side. So with that, we're going to balance the oxygen. So there's 2 oxygen on one side, 3 oxygen on another. There's an even-odd. So whenever you have an even-odd matchup, you got to look at the common multiple between the 2, and the common multiple is 6. So to make 6 oxygen on the reactant side, we're going to add a 3. So that becomes 6. And we're going to make 6 on the product side, we got to put a 2. And again, the iron gets distributed, or excuse me, the 2 gets distributed to the iron and to the oxygen. So now we have 4 iron and 6 oxygen. So you notice the oxygen is balanced. Now the iron is not, but we have 4 iron on the product side. We can very easily make 4 on the reactant side by putting a 4. That looks ugly. Fix that. A 4 on in front of the iron on the reactant side. So now we have a balanced chemical equation. Notice in all of these examples, we have not been changing the subscripts. That's a no-no. We do not change subscripts. Next, we have the decomposition of nitrogen monoxide. So again, we're going to start by determining the number of each type of element on both sides of the equation. So we have 1 nitrogen, 1 oxygen. We have 3 nitrogen and 3 oxygen. So you notice here that on the reactant side, we have 1 nitrogen and oxygen, and those are together in the compound. On the product side, we have 3 nitrogen and 3 oxygen, collectively from both products. So what we can do is, since they're both not balanced, and they both need 3, we can put a 3 in front of NO. So now this becomes 3, and this becomes 3. So now we have a balanced chemical equation. Now we get to the last example, and this is a level up. This is a little bit more difficult one. But we have ammonia plus oxygen gives us nitrogen monoxide and water. So again, we start by looking at the total number of each type of element. So we have 1 nitrogen, 3 hydrogen, 2 oxygen. And on the product side, we have 1 nitrogen, 2 hydrogen, 2 oxygen. So now we look, we see, hey, our nitrogen is balanced, but our hydrogen and oxygen are not balanced. And we see here that oxygen occurs in multiple reactants and products. Hydrogen only occurs in 1 reactant and 1 product. So our safest approach is to try to balance the hydrogen first. So you look at the hydrogen, we have a 3:2 ratio. Oh, excuse me, yeah, the oxygen is balanced right now. So the hydrogen, or actually the oxygen and the nitrogen are balanced, so the hydrogen is a 3:2 ratio. So we need to balance that, though, the hydrogen first. And since we have a 3:2, we have to look at the common multiple between 3 and 2, which is 6. So to make 6 hydrogen on the reactant side, we need to add a 2. So now our hydrogen becomes 6. But remember that 2 gets distributed to the nitrogen and to the hydrogen. And so that nitrogen now is 2. Now we move to the product side. To make 6 hydrogen there, we got to add a 3. And so now we have 6 hydrogen, but the 3 gets distributed to the hydrogen and to the oxygen as well. So now our oxygen has gone from 2 to 4. So now we look here, our oxygen is not balanced and our nitrogen is not balanced. But since oxygen is in multiple species, we want to do the nitrogen first. So since we have 2 nitrogen on the reactant side, we can put a 2 in front of the nitrogen here, and we get 2 nitrogens on the product side. But again, that 2 gets distributed to the oxygen and the nitrogen. So we have 2 nitrogen, and now we have a total of 3 oxygen and 2 hydrogen. So that's a total of 5. But we have a problem here. So we have a 5 on the product side, but we have a 2 oxygens on the, what's it called? The reactant side. So now we need to somehow get rid of this even odd combination, because there's nothing we can multiply by 2 to get 5. But what we can do is, if we go back and if we double the coefficients on the product side, then we get 10 oxygen. So what I mean is, instead of a 2, if we put a 4, and instead of a 3, we put a 6. The reason I'm doing this again is because we had 5 oxygen. If I double it, then we get 10 oxygen. And so now we have an even number of oxygen. Now, of course, our nitrogen and hydrogen have changed. We have 4 nitrogen and we have 12 hydrogen, but we can balance those again, because you see here we have 2 nitrogen and 6 hydrogen, so we just double this one as well. We get 4 nitrogen and 12 hydrogen. Again, we're doing this because originally we had 5 oxygen and 2 oxygen, and there's no way you can take 2 and multiply it by a whole number to get 5. So what we did is we doubled the product side to give us 10, and now we're balancing the reactant side with that double. And so we have 10 oxygen on the product side, we have 2, we can put a 5 in front of O2, and now we have 10 oxygen. So again, the only reason we doubled it was because we had a odd number on the product side of oxygen, an even number on the reactant side. There's no way you can multiply a number by a whole number to get an odd number if it's even. And so that's why we doubled everything. So the whole reason we talked about moles and we talked about balancing equation is so that we can get this mole to mole relationship between the reactants and the products. So when we have a balanced equation, that tells us, if we have this many reactants, how much product can we form? If we want to make this much product, how much reactant we should form. And what we get from the balanced chemical equation is called a mole to mole ratio. And a mole to mole ratio you could think of as a localized conversion factor for that particular chemical equation. So what you do is you take the coefficients, and that'll tell you, how many moles of water is needed to form this many moles of hydrogen. So when we look at this balanced equation, 2H2O yields 2H2 plus O2 means that for every 2 moles of water, we're going to form 2 moles of hydrogen. And for every 2 moles of water, we're going to form 1 mole of oxygen. So that's our mole ratio, our conversion factor of converting from water to hydrogen gas and water to oxygen gas. So in order to do this, you have to be in moles. So for example, we want to know, okay, if we have 5.8 moles of water, how much oxygen in moles can we produce? And so from the equation, we get that 2 moles of water give us 1 mole of oxygen. And we can write it as an equality where we say 2 moles of H2O equals 1 mole of O2. So now if we know the moles of H2O, we can convert it to moles of O2. Just like if we know the number of inches, we know that 1 inch is 2.54 centimeters, we can convert it to centimeters. We're doing the exact same thing, but on a reactant product level. So now we can convert the moles of H2O to moles of O2. So our ratio is 1 to 2. Since we're starting with water, water goes on the bottom, oxygen goes on top. And so 5.8 times 1 over 2 gives us 2.9 moles. If you want to see it in a train track form, I can do that as well. So we have 5.8 moles of H2O. For every, now since H2O is on the top here, it goes on the bottom. That's why in our ratio it's on the bottom. 2 moles of H2O, 1 mole of O2. And we get 2.9 moles of O2. And so that's how we use the mole ratio. Now if we want to know how many moles of hydrogen are produced by the same number of moles of water, we do the exact same thing, except now we use the ratio between hydrogen and water. So for every 2 moles of water, we produce 2 moles of hydrogen. So hydrogen goes on top in our ratio because that's what we want. Water goes on the bottom because that's what we're coming from or what we have. And so when we do this, 2 over 2 can be written as 1 over 1, and we get the same number of moles of hydrogen as there are water. So if we react 5.8 moles of H2O, we get 5.8 moles of H2. Now if we see this in another chemical reaction, so here we have a problem. It says how many moles of aluminum sulfide are produced when 8.5 moles of aluminum reacts with excess sulfur. So whenever you see the word excess in a problem for a reactant, that tells you, hey, there's more than enough reactant to use. Just worry about the other reactant, because the other reactant is going to get all used up. So if you kind of think of this as shopping, so for example, there's excess clothing stores in the city. You know, you're never going to run out of clothes in a clothing store, but when you go to purchase the clothes, the limiting factor is the amount of money you have. So you're going to run out of money first before you buy all the clothes that you want. The same thing happens when we have an excess reactant and one reactant that's not excess. So that what this means is the excess reactant is going to be remaining after all the other reactant gets used up. So we're going to have this 8.5 moles of aluminum. It's going to be all consumed in the reaction. Sulfur, don't worry about it. There's more than enough sulfur to take care of the aluminum. And so the first thing we need is a balanced chemical equation. And so from the balanced chemical equation, we can get the mole ratio to go from moles of aluminum to moles of aluminum sulfide. And notice here that 16 moles of aluminum produces 8 moles of aluminum sulfide. Oh, let me go back. So now we can set up our train track. We have 8.5 moles of aluminum. Now our mole ratio is, since we're starting with aluminum, it goes on the bottom, aluminum sulfide goes on top. And don't be alarmed if I put moles as MOLS. That's a common abbreviation for moles. That's have a habit of doing. So it's not like I'm misspelling it. It's just a common abbreviation for it. So again, moles of Al2S or aluminum sulfide goes on top because that's what we want. Moles of aluminum go on the bottom because that's what we started with. And so we get 4.25 moles of aluminum sulfide. Look at another example. So here we want to know how many moles of hydrogen gas are produced when 3.7 moles of B2H6 reacts with excess water. So again, when you see the word excess, that means don't worry about that particular reactant. So we don't have to worry about water. We just have to worry about B2H6. And we want to know how much hydrogen gas is produced when we have 3.7 moles of B2H6. So again, 1 mole of B2H6 gives us 3 moles of hydrogen. So since we're starting with B2H6, it's going to go on the bottom in our mole ratio, and hydrogen goes on top. So now when we draw our train track, we're starting with moles of B2H6. Since we're starting with B2H6, it goes on the bottom in our conversion factor. And hydrogen goes on top. And we get the moles of hydrogen produced. 11.1. And then lastly, we want to know in this equation how many moles of carbon dioxide gas are produced when 0.75 moles of O2 reacts with excess propane. So again, excess means don't worry about the propane, so we don't have to worry about that running out. We have more than enough propane to react. And so we want to go from moles of O2 to moles of CO2. And so we know that for 5 moles of O2 consumed, we produce 3 moles of CO2. And since we're starting with O2 in our conversion factor, CO2 goes in top, and O2 goes on the bottom. So whatever we're starting with goes on the bottom in our conversion factor or ratio. Whatever we're going to goes on top. And now we can do our train track. So we start with 0.75 moles of O2. Since we're starting with O2, it goes on the bottom in our ratio. And CO2 goes on top. So again, whatever we're starting with and the ratio goes on the bottom, it's coefficient. Whatever we're going to, it's in the ratio, the coefficient goes on top. And we get 0.45 moles of CO2. So again, you're kind of seeing the same process pattern that we're doing in this. So we have the moles of a reactant. We want to find the moles of a particular product. We need the mole ratio from the balanced chemical equation. Once we have the mole ratio, whatever we're starting with in the ratio, that coefficient goes on the bottom. Whatever we're going to, it goes on top. So now we're looking at this same equation again, but instead of giving us the moles of, for example, S8, it's given us the mass of S8. So we have this balanced chemical equation. It says calculate the mass of aluminum sulfide that is produced when 50 grams of sulfur S8, which is sulfur, reacts with excess aluminum. So now we're going to be doing something a little bit different. And let me kind of show you the pattern of what we're doing. So we're starting with the mass of S8. The first thing we're going to do is convert it to moles of S8. because in order to use the mole ratio, you have to be in moles. And then we're going to convert it to moles of aluminum sulfide. Once we do that, we're going to convert it to mass of aluminum sulfide. So again, we're just adding an extra 2 steps, one at the beginning and one at the end. But the core, the moles to moles, which we did, is still correct. So before we begin, I'm going to go ahead and calculate our molar masses. So for sulfur, and we'll do the same thing for aluminum sulfide. So now we have the molar masses of the reactant and product that we're investigating. So we can do this calculation. So I'm going to do it with the train track method so you can see. And I'm going to label this one as step 1, step 2, step 3. And I'm going to do it in this example, I'm going to do it in different parts to kind of show you each individual step. In the next example with mass, I'm going to do it all in one step so you can see the whole thing in a train track set up. And so what we're going to do first is we're going to convert mass to moles. And if you remember from the earlier in the lecture, we talked about how do we convert mass to moles, moles to mass. So in order to convert mass to moles, we need to divide by the molar mass. And again, this is step 1. So we have 50 grams of S8. We're going to divide by the molar mass, which is 256.5 grams of S8. And that's in 1 mole of S8. So this will give us the moles of S8. So now we have the moles of S8. We're going to go to step 2. In step 2, we're going to convert from moles of S8 to moles of aluminum sulfide. And from the coefficients, we get the ratio 8 moles of aluminum sulfide, 3 moles of S8. So since we're starting with S8, it goes on the bottom. We're going to aluminum sulfide, it goes on top. And now we can get the moles of aluminum sulfide. So that's step 2. Now step 3, we want to convert it to mass. So whenever we have moles, we have to multiply it by the molar mass. And now we get the mass of aluminum sulfide. So nothing different in the core of what we're doing than in the previous problem. The only difference now is at the ends, we're starting with mass and we're ending with mass. So we looked at this equation earlier, but we had moles. So here we want to calculate the mass of H2 that's produced when 25 grams of H2O reacts with excess B2H6. So again, we got more than enough B2H6 to react with the water. So water is going to get consumed first. So based on the mass of water, we can calculate the mass of hydrogen that's produced. And so what we need to do here is, again, if I write a little flow chart, we're going to take the mass of water, convert it to moles of water, and then we're going to convert it to moles of H2, and then to mass of H2. So moles, mass to moles, moles to moles, moles to mass. And so to do this, we're going to need some molar masses. We're going to need the molar mass of water. And we're going to need the molar mass of hydrogen. So again, I'll do this one in different steps so you can see each part. So we're going to start by converting the mass of water into moles. So we're starting with 25 grams of H2O. From the molar mass, the mass goes on the bottom, and moles goes on top. So again, this is step one. We get 1.39 moles H2O. So step two is to convert moles of H2O into moles of hydrogen. If we look at the balanced chemical equation, we see 6 moles of water produce 6 moles of H2. And so if we were to write this ratio, we would say 6 moles of H2 would be on top because that's what we want. And we're starting with water that goes on the bottom like this. So you can say 6 to 6, or you could say 1 to 1. It's the same ratio. So that's step two, converting it to moles of H2. So moles of H2O go on the bottom. Moles of H2 go on top. And so here the moles of H2 are 1.39 moles of H2. So that's step two. We convert from moles of water to moles of H2. And the last step is to find the mass of H2. And we're going to use the molar mass. So we got to multiply the moles by the molar mass to get mass. So 1 mole of H2 is 2 grams of H2. And we get 2.78 grams of H2. So if all of the 25 grams of water reacts, the most H2 you can form is 2.78 grams. So we're going to look at another example of what I want you to notice is that we're doing the same process or pattern every time. We're taking the mass of our reactant and converting it to moles, then using the mole ratio, convert it to moles of the product we want, and then convert it to mass of the product. Let's go look at another example. So here we have a combustion reaction. We have C4H10 plus O2 gives us CO2 and H2O. So we want to know how many grams of CO2 are produced when 910 grams of butane reacts with excess oxygen gas. So again, we're interested in the mass or the grams of CO2 produced when we have 910 grams of butane with excess oxygen gas. So the butane is going to get all consumed and there's going to be leftover oxygen gas. So again, if we were to draw a flow chart of this, we're going to take the mass of butane, convert it to moles of butane, then use the mole ratio to convert it to moles of CO2, and then we'll convert that to mass of CO2. So mass to moles, moles to moles, moles to mass. We're going to be needing some molar masses, so I'll go ahead and get those. So molar mass of butane, 4 times 12 plus 1 times 10. And we're going to need the molar mass of CO2. One times 12 plus 2 times 16 would be 44 grams per mole. So now we'll go ahead and get started with our train track. So step 1, we're going to convert mass of butane into moles of butane. So again, to go from mass to moles, we need to divide by the molar mass. So again, mass divided by molar mass gives us moles. So that's step 1. We found the moles of butane. Step 2 is we're going to convert it to moles of CO2. So to do that, we need the mole ratio. So from the equation, we know that 2 moles of butane produces 8 moles of CO2. Since we're starting with butane and we want to go to CO2, in the ratio, CO2 is on top and butane is on the bottom. So it's at 8 moles of CO2 are produced by every 2 moles of butane. So butane goes on the bottom and CO2 goes on top. Since we multiply what's on top, divide by what's on the bottom, we get 62.76 moles CO2. So that's the answer for step 2. Now we move to step 3. And we've got to convert moles to mass. So we know that 1 mole of CO2 is 44 grams. So we're going to multiply by the molar mass to get the mass of CO2. So that's 2,760 grams of CO2. So again, we wanted to find out the mass of CO2 produced when we had 910 grams of butane, reacts with excess oxygen gas. Our process is we're going to take the mass of butane, convert it into moles. That's step 1. Step 2 is we take the moles of butane, convert it to moles of CO2. That's step 2. And then step 3, we take the moles of CO2 and convert it to mass of CO2. So the same theme of the story here, we want to know the amount of ammonia produced when 105 grams of hydrogen gas reacts with excess nitrogen gas, and it gives us the balanced chemical equation. So we have 105 grams of hydrogen gas. We want to know how much ammonia is produced from this 105 grams of hydrogen gas. So again, if we were to make a flow chart, we're going to be starting with mass of H2. We're going to convert that to moles of H2, then convert it to moles of NH3, and then finally mass of NH3. So we're going to go mass to moles, moles to moles, moles to mass. We need a few molar masses for this problem. We need the molar mass of H2. And since we calculated it in the previous problem, I'm just going to put the molar mass, 2 grams per mole, and the molar mass of ammonia, so again, we have 3 steps. Just like that bear has 3 simple steps, you get your metal. We have 3 simple steps to get the mass of product. So the first step, we're going to convert mass of reactant into moles of reactant. So we start with 105 grams of H2. We got to divide by the molar mass, 2 grams of H2 and 1 mole. We get 52.5 moles. That's step 1. Again, this is moles of H2. Next, we're going to step 2, which is the converting from moles of H2 to moles of ammonia. We look at the balanced chemical equation. We see that 3 moles of H2 produce 2 moles of ammonia. So if we were to write the ratio, since we're going to ammonia, it's going to be on top, and H2 is going to be on the bottom. So now when we're converting from H2 to NH3, H2 goes on the bottom, and NH3 goes on top. Oops, wrong number here. Should be a 2 for NH3. 2 and 2. This will tell us the moles of ammonia produced. And we get 35 moles NH3. So that's the answer for step 2. Now we go to step 3. We want to find the mass of ammonia. So again, mass is equal to moles times molar mass. So the 17 goes on top. The mole goes on the bottom. And we get 595 grams of ammonia. So when we're starting with 105 grams of hydrogen gas with excess nitrogen gas, we can produce a maximum of 595 grams of ammonia. So overall, when we're doing these, what's called simple stoichiometry, we're always going to take the mass, convert it into moles of our reactant. Once we know the moles of the reactant, we can convert it to moles of the product that we want. Once we get the moles of the product, we're going to convert it to the mass of product. These 3 steps is being repeated over and over for these types of simple stoichiometry. Now, the most obvious question is what happens when it's not in excess? And so what we'll do then, and this is for a future lecture, what we'll do then is we'll determine the amount of product produced by each reactant and see which reactant produces the fewer moles of product. That's going to dictate how much product is produced. And that's where we look for what's called the limiting reactant. That's all for this lecture today.